Okay, so for today, let's talk about section 4.1, the extreme values of functions on closed intervals. Okay, so before we start to talk about the definitions and the theorems, I would like to go through a graph. Okay, so this is let's say an xy plane, and suppose this is a graph of a function f of x, and then also this is more introduction about my function. My function f(x) it is continuous, as you can see on the closed interval from a to e. Okay, so that's the preset. All right, so now look at this graph and then think about this question. At which point f(x) attains its largest value? You know. So for this problem, it shouldn't be that difficult, right? Because clearly, as you can see that at x equals d, in other words, corresponding value is f of d is the largest value, right? Across all the interval from a to e here. And a similar question, at which point function f(x) attains its smallest value? And as you can see that this is at point A, right? So this is f of A is smallest value. Okay, so and you can see, guys, when we see that the smallest value and the largest value here, you see these are global properties, right? Because from A to E is the playground for this function, and this is the largest value across all the intervals. Okay. And we do have a name for those two values. So at x equals d, we will see that this is where's this part? We have a name, this is called the absolute maximum. Okay, absolute maximum. And similarly at point A, we'll call this is called the absolute minimum. Okay, again, those two are global properties. Okay, and now let's shift our focus to the point of B, C, and E here. Okay, so you see point B, apparently it's not the absolute maximum for my function. However, if we, let's see, if we give an interval, that interval, let's see, it's around B and also include B, something like this. Do you agree that on this interval here, inside this interval, f of B is the largest one, right? So you see we can draw another two dashed lines, right, to do a comparison, right? As you can see that, f of B is the largest on this interval. Okay, and again, this largest value is only valid on this small interval, so it's a local property, it's not global. Similarly, if we draw an interval, let's see, around C, you will see that, okay, at x equals C, f(x) attains its smallest value, but only in this small interval, okay? And again, similarly, at x equals E, you can see that it's the smallest one, but you have to put an interval there, right? Okay, so those numbers here, as you can see, the B, C, E, we also have a name for them. And for B here, we have a name, it's called the local, since it's a local property, it's called a local max, okay, local maximum. And then for point C, we also have a name, it's called a local minimum, okay? And for point E, we also call it called the local minimum. And as you can tell, guys, if we use the definition related to, or use the idea related to local max or local min, you will see that at x equals a, it's also a local minimum, right? Although it's an absolute minimum. And similarly, at point D, it's also a local maximum, but meanwhile, it's also the absolute maximum. So that's about the main ideas about the extreme value of functions on a closed interval. We started with this graph. And the main task for this section is, okay, give you a function, and they also give you a closed interval, how to figure out the, let's see, the absolute maximum, the absolute minimum. Okay, and we do have a name for those absolute max and absolute min, which we call is part of the extreme value. Okay, so now let's look at some basic definitions here. If we have a function with a domain D, closed interval, and we have the definition about the absolute maximum. If fx is less or equal than f of c for all the x in D, then we claim that, okay, at x equals c, fx attains its absolute maximum. And similarly, we can define the absolute minimum if f of c is less or equal than f of x for all the x in this D. Okay, and both absolute max and absolute min, we have a name. It's called the extreme value. Okay, extreme value. And for this extreme value, like we just mentioned, it's a global property. Okay, while for the local max and local min, it's a local property. Okay, here is a definition. It's called the extreme value theorem, and it talks like this: if we have a function, and that function is continuous on a closed interval from a to b, and then guarantee that fx, the function, gonna have at least one absolute maximum and minimum. Okay, because sometimes you can have the absolute maximum in 2 points, right? So for example, something like this. Right? So in this problem, you can see I didn't draw those xy plane and then plot the points, but as you can see, guys, if this is x axis, this is y axis, fx attains its minimum. Let's see, absolute minimum, it's on the 2 endpoints, right? And then the absolute maximum, it's on those 2 points. So, but it's guaranteed if it's continuous on closed interval, fx gonna attain both absolute max and absolute min. Okay, and this absolute max and min might not be unique. Okay, but it's guaranteed it's gonna have the absolute max and absolute min. Okay, so I'll stop here and then we'll continue with 4.1.